One of the big themes I want to drive home in these lectures is how linear algebra enables you to see hidden structure. And over the next several lectures, we're going to be unpacking one of the big ideas in linear algebra, the notion of eigenvectors and eigenvalues. When I first learned about them, I didn't really realize how important they were and how useful they are to real applications. So I'm going to start our discussion of the subject with a few applications, and then we'll return to them as we unpack the concepts of eigenvectors and eigenvalues. All around us there are examples of systems, by which I mean a group of things that interact in interesting ways. For instance, the solar system is a collection of planets related by the laws of gravity. Often in a system, there are things that are in motion, and we often refer to such things as a dynamical system. The motion described doesn't have to be physical. It could also be relational, as in numbers of various things, like amounts of this or that chemical in a chemical reaction. Let's consider an example of a dynamical system involving the population of foxes and rabbits. Foxes and rabbits interact in interesting ways. Take a moment to think about how numbers of foxes and rabbits might relate to one another. Let's let f sub n denote the population of foxes at time n, and let's let r sub n denote the population of rabbits at time n, where n is measured in some unit of time like years. Now you might wonder why we don't use a letter t for time. We could, but in math we often like to use the letter n to note things that are whole numbers. And here the time parameter will be a whole number. Foxes and rabbits have seasons in which they breed, and so we imagine a situation where we measure populations at the end of every breeding cycle, just once a year. In the study of population dynamics, we're often interested in knowing the long-term behavior of populations. In other words, what happens to f sub n and r sub n as n goes to infinity? Now, in order to answer this question, we need to develop a model which describes how the population of foxes and rabbits relate to one another. So it's probably worth saying a little bit about mathematical modeling. Mathematical modeling is a process that uses mathematics to represent and analyze a situation or a problem that you want to understand. We may begin with a very simple model, but often we find a lot we can learn even from a simple model. That's because we make choices about what features belong in our model, and we incorporate only the most important ones. And then our results show how those features might influence the answer. So, the situation informs the model, and the model in turn informs what we can learn about the situation. And that in turn can inform a revision to the model if we wish to study it further. For instance, in our example of foxes and rabbits, a very basic model might begin by assuming the relationship between populations of foxes and rabbits from time n to n plus 1 changes linearly. So the vector f sub n plus 1, r sub n plus 1 depends in a linear way on both fn and rn. We might also assume that foxes eat rabbits, and so if there are no rabbits, the total number of foxes decrease from year n to year n plus 1, let's say by 40% each year. Similarly, if there are no foxes, we can expect the total number of rabbits to grow, let's say by 20% each year. Then our model might look like this. F sub n plus 1 equals 0.6 times f sub n plus 0.5 times r sub n, and r sub n plus 1 equals minus p times f sub n plus 1.2 times r sub n. Notice in the first equation, the coefficient of f sub n is 0.6, which says, in the absence of rabbits, when r sub n equals 0, we see that 40% of the foxes are dying in each year, so that f sub n plus 1, the population of foxes at time n plus 1, is 60% of f sub n, the population at time n. The coefficient 0.5 for R sub n shows how rabbits contribute to the fox population. This says that every 2 rabbits contribute an additional fox to the population in the next year, or said another way, prevents one from dying. In the second equation, if f sub n equals 0, the number of rabbits at time n plus 1 is 1.2 times the number of rabbits at time n. That's 20% growth each year. And we have written the coefficient of f sub n here as negative p. The fact that this coefficient is negative means that foxes contribute negatively to the rabbit population. And we've left p unspecified as an unspecified parameter that we will call the predation parameter, because this is the term that shows how quickly foxes eat rabbits. The larger this term, the more rabbits are eaten by foxes. Later on, we'll explore the behavior of the system in several instances of p. Now, this is a simple linear model. It's surely not an exact description of what's going on in lots of ways. First of all, I've made up the coefficients for our toy model, but if you were determined, you could try to use data to estimate those coefficients. Also, rabbit and fox populations are always whole numbers, but that's not true of this model. And even if we ignore that, the actual real-life fox-rabbit population dynamic is almost surely not linear. However, it's probably approximately linear, so if we explore this model, we'll likely get some insight that will be valuable nonetheless. Let's rewrite our linear model as a matrix equation. We'll call the population vector x sub n, which has components f sub n and r sub n. Then our model is telling us the vector x sub n plus 1 is some matrix A times the vector x sub n. The matrix has entries 0.6, 0.5, minus p, and 1.2. The question we're interested in is this. Given the initial populations at time 0, what is the long-term behavior of the population of foxes and rabbits at time n as n goes to infinity? In particular, do the populations grow forever or die out? And what will happen as we vary the predation parameter? Now you'll notice that x sub n plus 1 is written recursively in terms of x sub n. So if x sub 1 equals a times x sub 0, then x sub 2 equals a times x sub 1. But that's just a times x sub 0, or a squared times x sub 0. So if we repeatedly use the recursive formula on x sub n, we can inductively see that x sub n will be a to the nth power times x sub 0. That's nifty, but now the question becomes, how do we compute a to the nth power? Can we do it quickly? We'll return to this example once we've developed the machinery. But what I want you to notice now is that answering the question about fox and rabbit populations has led, in a very simple model, to the problem of how to compute powers of a matrix. And we'll soon see how eigenvectors and eigenvalues can help us. Let's look at another sample application where eigenvectors and eigenvalues can give us insight. This example comes from analyzing networks. Think of a bunch of nodes with edges between some of the nodes. For instance, the nodes could be a bunch of website locations, and the edges could signify which pages link to which other pages. In fact, we can draw arrows on our edges to tell if the linking goes in one direction. In the simple example I've drawn here, suppose there are only 4 nodes, A, B, C, and D, representing web pages in a small network. A is connected to B, B to D, D to C, and C to A. And in each instance, the links go both ways. There's also a link from web page B to web page C, but not vice versa. It's convenient to represent this network and its connections using an adjacency matrix M, which is a matrix of zeros and ones. An entry in this matrix, M sub ij, is 1 if and only if there's an edge going from I to j in the network. You can see in this example the matrix M is a 4x4 matrix. You can see from the 1 in the second row and third column that there is an edge from B to C, but because there is a 0 in the third row and second column, there is no edge from C to B. Notice that the matrix M would have been symmetric about the main diagonal if all the edges were bidirectional. One of the coolest things I remember learning when I took linear algebra was the following fact, that if you raise the adjacency matrix to the power n, then the entries of m to the nth power actually have an important interpretation. The ijth entry of m to the nth power is notated by m sub ij with superscript parenthesis n. It will actually tell you the number of paths that go from I to j in exactly n steps. Really? That's amazing. Let's see why, and then do an example. We can get a hint from looking at the row-column formula for matrix multiplication. For then m sub ij superscript parenthesis 2, which is the ijth entry of m squared, is defined to be the sum of m sub ik times m sub kj when summed over all k. Notice that this product m sub ik, m sub kj is only non-zero when there exists an edge from I to k and one from k to j. And in that case, the product is 1. So this sum counts the total number of steps of length 2 that go between I and j. In a similar fashion, if you wrote out what the ijth entry of m cubed is, you would see that it is a double sum over all pairs of possible intermediate nodes k and l of the triple product m sub ik times m sub kl times m sub lj, which is only 1 and non-zero when all three edges exist from I to k, k to l, and l to j. So you could show by induction, if you wish, that this kind of thing persists in general. Now let's look at an example. Consider the 4-node web that we were analyzing earlier and take the cube of the adjacency matrix M. If I've done my calculations right, then M cubed should be this matrix. Notice that this is a matrix of 16 entries, one for each pair of nodes from A, B, C, and D. The entry 1 in the first row and fourth column corresponds to how many paths of length 3 start at node A and end at node D. If you look at the figure, there is indeed only one 3-step path, going from A to B, B to C, and then C to D. In the third row, third column of M cubed, we find a 2. This means there must be 2 paths of length 3 that start at C and end at C. From the figure, you can see what these are. One path goes over the top, C to A to B to C, and the other goes through the bottom, C to D to B to C. Now look at the 0 in the third row, second column. This says there are no 3-step paths from C to B. And indeed, if you look at the network, there are some 2-step paths and some 4-step paths, but there are no 3-step paths. Let's do one more example. Look at the 4 in the third row, first column. This says there are 4 3-step paths from C to A. For instance, there's the obvious one, C to D to B to A. But there's also C to D to C to A, and there's C to A to C to A. Can you find one more? This interpretation of a matrix product is pretty nifty. Even if it wasn't good for anything, it would still be nifty. But this idea does have some cool applications. If I want in the long run to understand where the traffic over the network is, I could just start on a random web page and then look at how many n-step paths there are that lead to each of the nodes in the network. So start on a random page would be to start with an n-dimensional vector v with 1 over n in each component. then v times m to the n would give a vector whose jth component gives the average number of paths that start somewhere and end at page j. The relative sizes of these numbers give some sense of how likely it is to find a random surfer at page j after randomly clicking links n times. Such numbers would be a very crude way to rank the importance of web pages. So what I've just shown you again is the importance of knowing how to find matrix powers efficiently. Moreover, I'm interested in not just knowing what m to the nth power is, but also in seeing what happens to the untrees of m to the n as n goes to infinity. Now, taking a matrix A to a very large power could involve lots of calculations, but there may be some situations where the calculations simplify greatly. The best way to see this is to think about the associated function that takes a vector x to a times a vector x. Recall, this is a linear transformation which sends 0 to 0, but generally moves vectors around. So x and y go to ax and ay, and these may be pointing in different directions than x and y. But what if, on some vector, call it w1, we have the special property that a times w1 points in the same direction as w1? That would mean a times w1 is a scalar multiple of w1. In this case, let's suppose that multiple is 2. If so, then we will call such a special vector an eigenvector of A. An eigenvector of A has a property that when you apply the linear transformation that multiplies the vector by A, then you just get a scalar multiple of the eigenvector. The multiple you get is called the eigenvalue, in this case 2. And for eigenvectors, the action A is very simple. For instance, if A times W1 is 2 times W1, then W1 is an eigenvector for A, and 2 is its eigenvalue. Then A to the n times W1 will just be 2 to the n times W1. What would normally be hard, computing the nth power of A times a vector, is now very easy for special vectors called eigenvectors, since in that case A to the n times the eigenvector can be computed as an eigenvalue to the nth power times that eigenvector. We asked, what if there were such a vector? Of course, we'll need to explore when we can say that such vectors exist. This is a good situation. An even better situation would be, what if there were a second vector, w2, which behaved like an eigenvector? Let's say A times w2 equaled 7 times w2. And still better than that, what if w1 and w2, the eigenvectors we've identified, formed a basis for R2? That would be a dream scenario. Because then for any vector v, computing a to the nth power times v would be easy. Notice that I said in our dream scenario, the computation would be easy for any vector, not just eigenvectors. Here's why. If w1 and w2 formed a basis, then given any vector v, we could write it as a linear combination of w1 and w2. Let's say a times w1 plus b times w2. Then a times the vector v would be a times the quantity aw1 plus bw2. But by the eigenvalue property, this is just a times 2 times w1 plus b times 7 times w2. Notice that if I were to multiply this result by a again several more times, the eigenvector property would pop out another factor of 2 and another factor of 7 for each multiplication by a. So then, the nth power of a times vector v equals little a times 2 to the n times w1 plus little b times 7 to the n times w2. This is much easier to compute than multiplying matrices. And both the previous applications, ranking web pages and looking at the long-term behavior of foxes and rabbits, depend on this kind of calculation, looking at a matrix to the nth power times a vector. So now we must ask, when do we achieve the what-ifs we asked about earlier? When is the dream scenario true? We'll need to figure this out in future lectures. Let's now define an eigenvalue and eigenvector carefully. Here's a definition. Given an n by n matrix A, we will say a number lambda is an eigenvalue for A if A times V equals lambda times V for some non-zero vector V. If such a vector exists, we'll call it an eigenvector of A corresponding to lambda. We'll refer to the equation AV equals lambda V as the eigenvector equation. Let's note a few things. First of all, it's traditional to notate an eigenvalue using the variable name lambda. Lambda is just a number. It could be 0 or negative or positive. However, we will prohibit letting an eigenvector be the 0 vector because then the eigenvector property would hold for any matrix and any eigenvalue, which would be kind of dumb. So we don't let that happen. In the coming lectures, we'll see how eigenvectors and eigenvalues can help us compute matrix powers quickly and provide still another way to test if a matrix is invertible. They will help us understand the linear transformation x goes to ax, and we will of course return to the examples we opened this lecture with to try to understand more fully what eigenvectors and eigenvalues are. These hidden structures are now revealed and they'll give us a lot of insight. But how can we find eigenvectors and eigenvalues? We'll do this carefully soon, but it may help us to sketch the broad ideas here so that you have some time to let the ideas germinate. We'll begin by using a little reasoning involving matrix equations. How do we find some vector that satisfies some equation like AV equals lambda V? It may seem that we don't have enough information, especially when you realize we also don't know what lambda is. Also, another obstacle here is that the left side is a matrix times a vector v, and the right side is a number times a vector v. So it would seem hard to manipulate this equation to isolate and solve for lambda and v. Okay, now that I've stated the obstacles, let's see what we can do. The first thing we can do is to make both sides of the eigenvector equation a matrix times v by simply introducing the identity matrix on the right-hand side. We can insert it without affecting anything since lambda times v equals lambda times the identity matrix I times v. Now, grouping lambda times the identity matrix I, this is just a diagonal matrix with lambda on the diagonal and zeros everywhere else. The strategy now is to move everything to the left side and factor the vector v. Doing that, we see that a minus lambda I times v equals the 0 vector. Or said another way, since a minus lambda I sends v to the 0 vector, then the vector v is in the null space of the matrix a minus lambda I. Since v was an eigenvector, we assumed eigenvectors are non-zero, then we will see that there's a non-trivial element in the null space of a minus lambda I. So the nullity of a minus lambda I is at least 1 and can't be 0. Or, said another way, a minus lambda I times v equals 0. That equation has more than just the trivial solution, v equals 0. By the invertible matrix theorem, this means that the matrix a minus lambda I is not invertible. And also by the invertible matrix theorem, this means that the determinant of a minus lambda I is 0. So we can solve for lambda so that the determinant of a minus lambda I is 0. Notice that we have now isolated the unknown eigenvalue lambda from the unknown vector v. There's no vector v in this equation. But if you take the determinant of a minus lambda I you'll find that it is a polynomial in lambda, so its roots will give us the eigenvalues we desire. There will be n of them, and sometimes they may be complex roots, and sometimes they may be repeated roots. Once we've done that, then for each lambda we must find non-zero vectors in the null space of A minus lambda I. These will be the eigenvectors corresponding to the eigenvalue lambda. That's a sketch of how we can solve the eigenvalue equation. In the next lecture, we'll do several examples to flesh this reasoning out. Let's return to foxes and rabbits momentarily. We certainly don't have enough tools yet to answer the question about long-term behavior of foxes and rabbits. Those tools will be built over the next couple of lectures. But we can at least think through the meaning of an eigenvector and eigenvalue. Recall that vectors for foxes and rabbits consist of the two population totals. If we have a special vector v, for which AV equals lambda v, then v is an eigenvector, and its components represent fox and rabbit populations, which, after each successive time step, remain in the same relative proportion to each other. All that happens is that both populations get multiplied by the same factor lambda. And if lambda is greater than 1, the populations are growing. And if lambda is less than 1, both populations are shrinking. And if lambda equals 1, then the populations are remaining constant. So eigenvalues can tell us something about the contraction or expansion of the eigenvector that it is associated with. Indeed, the eigenvectors and eigenvalues of a matrix are hidden structures that are now revealing themselves, and they can tell us a lot of information about a matrix and its behavior. We'll see more in the next lecture.